Alright everybody, welcome back. Mr. Martin here. We're going to start 8.2 functions and their graphs. So we're going to be getting back into some graphs and talk about domain and range a little bit more, and then we got a couple new things, this constant, increasing, and decreasing intervals. Okay, so there will be some new stuff here. There's a lot of vocabulary and a lot of little rules. So this is something you might want to go over several times as we are working throughout this section. Alright, jumping into our vocab, a lot of this might be familiar to you, but it's very important that we talk about it again, just because we're going to be using it in this section. So our domain is all of the x values that are in the graph of the function. So when I try to remember this, I always just say domain x, domain x, domain x a bunch of times, and then it kind of sticks, and I know that I'm talking about the x values when I think about the domain. And then on the other end, our range is all of the y values that are in our graph. So range y, range y, range y. However you want to remember it, just remember that the domain is the x and the range is the y values. Okay, this part might be new. We have what we call a minimum and a maximum. And the minimum is our lowest y value. Okay, so we are thinking about the y values with our minimum and our maximum, and the maximum is the highest y value. Okay, moving forward, x-intercept and y-intercept, we've seen these before. Just remember the x-intercept is where we cross the x-axis, and the y-intercept is where we cross the y-axis. Okay, and then now this last piece, this is a big chunk here. I'm going to draw this little bracket. If I can make it nicely, boom, right there. These three are very important. We have what we call increasing, decreasing, and constant, and this is a way for us to describe what is going on in the graph as we look at it. And the reason why I say these are important, and I drew this little bracket here to include all three of these, is because we want to think of these in terms of x. Okay, so if we take a look, a function is increasing when the x value increases and the y value increases. So both of them are increasing. A function is decreasing when the x value increases, so just like the other one, the x value increased, but here the y value is decreasing. And then a function is constant when the x value increases, so increases again, but the y value remains the same. Okay, so something that might be helpful to maybe write down somewhere on your paper, when we talk about increasing, decreasing, or constant, we are thinking in terms of x. Alright, so I wrote this down here. When describing intervals, think of terms in x. So the only thing that we really are going to be using in terms of y is the range. Everything else we're labeling through our x values. So this is important, and the more you practice it, the more you'll see that it makes sense. Alright, moving forward, I have some more graphics for you here. A vertical line test is something that we use when we're looking at something graphically to determine if it is indeed a function or not a function, and what helps us identify if it is not a function is this vertical line test, meaning that if we cross the graph more than once, then it will not be a function. So we are not allowed to cross the graph twice. So here on this image, if we went straight down with this vertical line, it would cross this graph in two different points, and then it would indicate that it is not a function. So this is very helpful when you are looking at different types of graphs and trying to identify if it is a function or not. Alright. We also have different types of notation and symbols used. So here we have inequality notation, we have a number line, and we have an interval notation. And we are going to be using the example of the interval from 1 to 2. Okay, so we have seen inequalities and number lines, and I've talked to you guys a little bit about interval notation before. This is actually my favorite to use. Seems a lot quicker to write and looks a lot cleaner in my opinion. But the things that you need to remember are a closed circle means we include, an open circle means we do not include, with an inequality. The underline means we include, without means you do not include, and then if we use interval notation, the square bracket means we include, and the parenthesis means we do not include. So here, if we are including 1 going all the way up to 2 but not including it, we would square bracket next to the 1 and then parenthesis around the 2. And of course you can always write a compound inequality using the underline, saying you're including 1 but you are not including 2. Okay, so it's very important that you have a handle on using the different types of notation. This is how we're going to answer most of our questions in this section. Okay, another thing that's important to understand is how we use the notation with infinity, because remember, we cannot actually reach infinity. It is impossible. It just goes on and on forever. Hence why I always have you draw arrow tips on your graphs, because if we are indicating that we are going on all the way on forever, then we would need to use some sort of infinity. This is going to the right, so of course we would have a positive infinity. If we were going all the way to the left, we would have a negative infinity. So those are two different things. So when you do interval notation, you should always have a parenthesis next to the infinity. It should never be a bracket. Okay, and then when we have two intervals, this is something that we're going to use also. There's this symbol right here. It's called union. Okay, and what that union symbol means is we are having two or more intervals, and we are just describing what is happening. So remember, we read from left to right. So this graph is saying that we are going from negative infinity all the way to 2, and we are including it. And we are also not including 3, but we are going all the way to infinity. Okay, so this is describing what is happening with this graph right here using that symbol union. So this is important to remember as well. Alright, so example number 1, I'm going to do a couple of these with you. We want to use the vertical line test to determine if these are functions or not. Let me get my line going right here. So what you would want to do is you could just draw a line at any point and just see if it crosses once or if it crosses more than once. So like here, I'm drawing these lines. Each time I draw a vertical line, it only crosses the graph once. So would this be a function? Yes. Okay, so let's try it again here. If I just pick a spot, oh, looks like it is crossing at 2 points. So this vertical line touches 2 points. That is a no-no for function land, so this would be a no. Okay, and then this one, this line looks a little bit steep, but if you draw a line down it, it's only going to cross once. Here it'll only cross once. So is this one a function? It sure is. And then this next one, well, you can kind of see here, yep, crosses at 2 points. So we are no bueno. Okay, now of course if you were to draw the vertical line right here, okay, at the tip of that arc right there, that semicircle, it would only cross once right there, but the rest of the function, it crosses more than once. So that would indicate that we are not a function. Alright, I want you to pause the video right here, try these next 4 on your own, and then come on back and see what you got. Alright, welcome back. So I got yes, no, yes, and no. So remember, if we drew some lines here, it would only cross once. Any type of circle will never be a function because you're going to cross at 2 points. And the one that looked a little bit different, probably this vertical line here. If you just drew a vertical line down this vertical line, you're like touching every point on that line. So that's way, way too many points, and that would not be a function. Alright, let's go to example number 2. We got this graph right here. It says using the graph below, we want to answer all of these questions right here. So I'm going to go through all of these with you. One thing you want to take note of is the lack of arrow points. So does this graph go on forever? No, that's why I was super picky about drawing arrow tips, because this actually means something different. Okay, so we want to take a look at each of these points here. Are they open or closed circle? Looks like they're all closed circles. So any of these points here we're going to include. Okay, So let's just start chugging away. So we got x-intercepts. Remember, this is where we cross the x-axis. So looks like we cross the x-axis right here, going from left to right. So our first point, remember these we want to list as ordered pairs. So we got a x-intercept at -5, 0. Okay, and then going forward, we also have one at -3, 0. Remember, and it's okay to have more than one. And then going to the right more, we also have one at 3, 0. Okay, so not too bad. These are easy to find. All right, y-intercepts. Now we are looking at the y-axis. Where does the graph cross the y-axis? And we have one at 0, -3. So remember, a y-intercept is when x is 0, and an x-intercept is when y is 0. All right, so now with the minimum and maximum, remember this is the highest and lowest y value. So we want to look on our graph, where does it reach the highest y value? So it looks like this is our highest y value here at this point right here. So we want to ask ourselves, what is this point? And this point is going to be 5, 4. So our maximum is at 5, 4. Okay, and then for our minimum, we want to look at our lowest point. We got a low point here, but this is even lower. So this point is 1, -4. Oops. 1, -4. And remember, our graph will read from left to right for the domain, and then the range we read from bottom to top. So left to right, bottom to top. So here for the domain, I want all of my x values from left to right. So what is my furthest x value to the left? Well, that's going to be -7. So if I wanted to write this in inequality notation, I would say -7. Okay, I am including it because I have a solid dot here. So this is going to be x is greater than or equal to -7. Okay, and I'm going all the way to +8. And again, I have a solid dot, so I am including +8. Okay, so this is inequality notation. If I want to use interval notation, which is my favorite, I would do square bracket -7, comma, +8. Okay, remember, left to right. All right, now for the range, remember we go from bottom to top. So what is my lowest y value? That is going to be -4. So -4. And all of these are solid dots, so all of these are going to be equal to. And then I want to ask myself, what is my highest y value? And that is +4. So remember, the range are your y values. So make sure you put a y here if you are doing inequality notation. And we said we are going to +4. And that's also why I think interval notation is a little easier. I don't have to remember my x or y. I'm just going from -4 to +4 for my range. All right, and then it asks for the constant. And remember, constant is where my x values are getting bigger, but my y value remains the same. And you can kind of think as constant as just a straight flow. Where does the graph look like it is leveled off at? Where is it just traveling straight? Here we're up at an angle, 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 angle. Here we are going from left to right. So 6 to 8, my values are getting bigger, but these y values are not going up or down. They're staying exactly the same. So I am constant from, and I'm just going to do the rest of these with interval notation. I am constant from, remember, I'm always thinking in terms of x. So from 6 to 8 is where I am constant at. So from 6 to 8. Okay, and then now I am talking about decreasing. So from left to right, it looks like my graph is going up, so I don't want that. But now I have a change at this point. And what is this point? This point is at -4. Remember, I am thinking about x values. So from -4, it looks like I'm going to start going downward. And I'm going downward all the way to what x value? To my x value of +1. So from -4 to 1, I am decreasing. Is there anywhere else on this graph that is decreasing? Well, I went back up, and then from here to here, it looks like I'm going down. So this is where I'd want to use that union. and then I am decreasing from +5 to +6. Remember, think in terms of x. All right, now let's find out where it's increasing. We are starting from -7, and we're increasing all the way to +4. Okay, and then I have another part of increasing where I need to use my union, and I'm going from 1 all the way to 5. Okay. All right, now we have this thing called positive. So I want to find out where all of my graph is a positive value. So I might have several sections. So the positive means I am above the x-axis. So I guess you could think in terms of y for this one. And then negative would be below the x-axis. So right now my graph here is all the way below, and this is where I would start being positive, from -5 to -3. So I might have a couple of these, -5 to -3. And then now it's negative, negative, and then I am now positive again from 3 all the way to 8. And then now let's do the negative. So negative, I am starting out at -7, and it is negative all the way to -5. And then negative from -3 to +3. Alright, so those are all of the intervals that we have on this graph. And then just like in the previous section, we have some function notation. It is asking you to find some of these values, whether they are the x or the y value. Remember, if it shows inside the parenthesis, that is my input, so I'm giving an x value. I want to find what the y value is. So this is asking, what is the y value when x is +4? So if I'm at +4, I would just find the graph. In this case, I need to go up. So when x is 4, y is equal to +2. Alright, when x is +2, y is equal to -2. When x is -8, well, if I go up or down, I have no graph. So this one we would say does not exist. Okay, there is no y value that exists when x is -8. What about when x is +8? Yep, we got a value here, 2. Alright, remember also when it's on the outside, this is when y is equal to this value, so I'm trying to find x. So here I would want to say x is equal to, so let's check it out, -3. What is x equal to? Well, right now this is the origin, so at -3, x is equal to 0. X is also equal to, what is this? Maybe 1.5. We can approximate, so 1.5. And then even if you want, you could do approximately. And it looks like those are the only values. All right, at -2, x is equal to -1. And it is also equal to +2. And then our last one, what happens when y is equal to 7? Well, if we went left or right, there is no graph here, so we have another does not exist. All right, now I know there's a lot of stuff to answer, but it's really just kind of eyeballing the graph and getting comfortable with that notation. As long as you know what you're doing, you should be pretty accurate and good to go. So with that said, example number 3, I want you to pause the video here, come on back, and see if you got the same stuff that I have. Alright, pause the video. Alright, welcome back. So this is what I got for this graph right here. I want you to just go ahead and take a look at all of these answers, make sure that yours match up. Remember, the big thing though is you got to have that notation correct if you are using interval notation. Putting a square bracket where a parentheses should be is going to be incorrect. So if you look here, we have an open dot at -6, so that's why my domain has a parenthesis at -6, and it's going all the way to +8 that has this solid dot, and we are indeed including that 0.8. So that domain is from -6 but not including. Okay, and then the range, our lowest value at -4 all the way to our highest value at 7, including both of those points. So take a look at this again and then go from there. All right, let's go to example number 4, which I have a typo. So let's fix that. So this should be number 4. Okay, we have this graph here, and it says here's a travel graph of Sion's journey from her house to the library and then back to her house. Our y-axis is the distance away from her house, and then down here we are talking about time, and it looks like these intervals are going by 10 minutes, because if we go from 9 o'clock to 9:30, we have 2 tick marks in between, so this is probably 9:10, 9:20, 9:30. So we got a couple questions here that we want to answer, so I'm just going to type these in so it looks easier for you guys to read. Let's choose a font that will fit, probably this. So the first question asks us how far is Sion from her house at 9:30? So this is where we would want to look. Well, down here at 9:30, if we go up to the graph, we want to look at our y-axis, and this is in kilometers. So if we just trace back to here, it looks like 10 kilometers away. So we would want to say 10 kilometers away. Okay, and then let's actually change this color. There we go, looks good. Alright, and then at what time did Sion arrive at the library? Well, if we take a look, the library is probably the end of the graph, right? It doesn't indicate how far away the library is, but if we look at the context of the graph, we know that she went to the library and then back to her house. So the end destination would be her library. Unless she lied, of course. But here it looks like the end distance is 20 kilometers. So we want to find out when she got to this point right here. And if we trace this down, it looks like 10 o'clock. So she arrived at the library at 10 o'clock. And our next one says, how long did Sion stay at the library? Well, we know that staying put, we're not going to travel any distance, but what will continue to tick on, as it always does, is time. So if we look for our constant, that lets us know that we have not moved any distance, but time has continued to pass. So we're looking at around from 10 o'clock to 10:30. So how long did she stay? She stayed 30 minutes. Not much time at the library. She probably could have got a lot more done. Maybe she got a phone call and had to rush home or something. So our last one, did Sion take a break while walking to the library? And if so, how long was her break? So it looks like, you know, she's traveling. She left at 9 o'clock, but then from 9:30 to, what is this, 9:40, looks like time had passed with no distance. So yes, I would say she took a break. So yes, she took a break and it lasted 10 minutes. All right, and our last example, which again has another typo, this should be example number 5. Let's go ahead and change that. Example number 5. Okay, so we got this graph here, and it says there's a little storyline here. It says Mr. Martin was making a trip to the local sneaker boutique. On his way, he stopped for some doner kebabs and then proceeded to the store. Use the graph below to answer the following questions. So I want you to pause the video here and try to give some of these a go and see if it matches up to something that I would put. Okay? All right. All right, welcome back. So this is what I came up with. What time did Mr. Martin stop for food and how long did he stay here? Well, we only have one constant on the graph, so this is probably where he stopped for food. And that was from 11 o'clock to 12 o'clock, so he stayed for 1 hour. How far away was the sneaker boutique? Well, the end destination is probably our maximum, so here's the highest point, so it looks like it is 60 kilometers away from his house. And then it asks in kilometers per hour, how fast did Mr. Martin travel to the sneaker boutique from the restaurant? Well, he stopped eating right here, and then he got to the sneaker boutique right here. So we want to ask ourselves how much distance was covered and how much time had gone by. So from here, it looks like we're at 30 kilometers, and then here we are at 60 kilometers. So from the restaurant to the sneaker boutique was 30 kilometers. And he traveled that distance from here to here, which is only 30 minutes. So if he went 30 kilometers in 30 minutes, but I'm looking for kilometers per hour, I would need another 30 minutes, right? So if I had another 30 minutes at 30 kilometers, that would give me 60 kilometers in 60 minutes, meaning 60 kilometers per hour, okay? Which is faster than you can drive on base. How much time did Mr. Martin spend at the sneaker boutique? Well, he got there and then he immediately turned around. So he actually spent no time there, maybe a millisecond if you really want to be picky. But the way that the graph indicates, it looks like he got there and then he immediately turned around. So what might be a reasonable explanation for what happened at 12:30 when he reached the sneaker boutique? It could be something like maybe they were closed, so he just turned around, or he realized he left his wallet at home and had to go back and get it. But as you can see, he went and got back home, and maybe he was lazy or he had to take care of the baby and just didn't get to make it back out there. All right, so that wraps it up for this this section here. Please try the practice. Remember, practice makes perfect, or perfect practice makes perfect, is how the saying goes. Ask a friend, ask your teacher, ask for help, do the work, and we will catch you on the next video. I enjoyed this one. I hope you did too. All right, peace out.